Previously, we've summarized everything about kinematics. Now let's move on to statics. In statics, we talk about balance of forces, right? So we need to talk about force. The first one I would like to talk about is the body force. Here is considered as a body force density. You can consider it as a weight of the body. In the initial configuration, let's take a small volume, and it has a body force density of B0. In the current configuration under deformation, this small volume changed to dV, and it has a new body force density B. So B0 and B are body force per unit volume in the initial and current configurations, respectively. So there must be something that is constant across the different configurations, and that is the total sum of body force or the weight of this body. So we are going to make use of this formula, which we obtained in the kinematics part of this lecture, and this is dV equals to determinant of F times dV0. Now let's calculate the total body force on the left for the initial configuration, and then calculate the total body force on the right for the current configuration. So on the left we have the integral of B0 over the initial configuration, and on the right we have the same but integrated over the current configuration. They must be equal, and for each this small cube here, we also have the conservation of the total sum of force. So basically for each small cube we can write B0 dV0 equals to B dV. You just imagine that now we are going to have the entire omega being the same as this small cube. We would then arrive condensed into this equation. And because we have the relationship between dV and dV0, we can then express B0 in function of B through the determinant of F. However, the body force is usually ignored in quasi-static analysis, but for the purpose of completeness, I include the discussion of body force here for the lecture. Next, we are going to talk about stress. So this is of crucial importance for structural analysis. Stress. What is stress? Stress is defined as intensity of loading. In terms of unit, is force per unit area. It could be attraction or it could be a pressure. Now, so we need to define an area. Let's say it's dA0 in the initial configuration with a normal N0. And through deformation, it changes to dA with a normal of N. Now, let's say on this current deformed configuration, this surface has a loading as a force dF. So if you make a small cut, then this, because of the internal force balance, there is a reaction force on this surface, which is dF. And then we know that dF, which is a force over this area, equals to the traction over this area times the area. Traction is the force divided by area. And when the dA is very small, we can simply multiply the traction by the area. And from Cauchy's theorem, we know that the traction on an area with normal N equals the Cauchy stress tensor, or matrix, you can imagine it, multiply with the normal of this surface. This is from solid mechanics. Now, from balance of angular momentum in your previous solid mechanics course, you know that the Cauchy stress tensor is symmetric. So these are the things that covered previously in senior year undergraduate solid mechanics courses. Now, the Cauchy stress represents the true stress in the current configuration. The stress tensor, or in implementation is a matrix, is symmetric. The problem, however, is that all these quantities are defined in the current configuration, which is unknown to us. Previously, in the linear FE modeling, we never need to worry about this because we always assume the current configuration to be the same as initial configuration, which we know. But now we can't do it anymore. So the objective here is to find the counterparts in the initial configuration. Right? We'll try to fill in this part of the slide, which has a one-to-one correspondence with these terms on the right. The first thing we need to do is to bring out the formula that we intend to use to relate the NdA with the N0dA0, which is a nonsense formula. We'll put it here because we're going to use it. And now I'm going to apply the same force but on the undeformed initial configuration. This is what we call the engineering definition of stress, T0, because when we perform any experiment, we just divide the force by the original area, cross-sectional area, even though we know that the area must have changed under deformation. So this is the engineering definition of stress. We divide, so T0 would equals to dF, which is the actual force, divided by the original area. Now, I define a new matrix, or to be more specific, a tensor, which gives me the engineering stress if I multiply it by N0. So this is a one-to-one correspondence with the Cauchy stress tensor here. All right, so I try to construct a new stress tensor which gives me T0 through multiplication with N0. And the way to construct it is to try to find the relationship through this equation, right? Through dF. dF is the same across the two configurations. And now I have N0 dA0 on the left and N dA on the left. I can connect the two with Nansen's formula, which means that now I replace what's written here underneath. Then this one and this one would cancel out each other. What I'm left is that P on the left would be equals to tau times determinant of F and F transpose inverse. But determinant of F is a scalar, I bring it forward, I obtain this expression. And because I have tau being symmetric, and tau I can express it as P times F transpose divided by a scalar, determinant of F. So if tau is symmetric, P times F transpose must also be symmetric. So P times F transpose equals its own transpose, which is F and P transpose. However, this would mean that P itself is not symmetric. So P here, I've talked about it, but I've never given this name, so it's called first Pure Kirchhoff stress tensor. So its product with its multiplication with the N0, which is the normal of the cut plane in the initial configuration, gives the engineering stress. It is not symmetric, so it's good in the sense that it has one leg in the initial configuration, so it multiplies with the vector defined in the initial configuration, and the other leg in the current configuration, because when you multiply it times and you times the area dA0, it gives you the force defined in the current configuration, and it's not symmetric. So whenever you have a stress tensor being not symmetric, it is very undesirable, because previously we have a symmetric strain tensor, which is the Green-Lagrange strain, and now we have an unsymmetric stress tensor. Then this will mean that we will need to have a constitutive matrix which is unsymmetric if we were to use this stress measure, and this is obviously unwanted. So then people come up with a new definition of stress tensor, which is called second Pure Kirchhoff stress tensor. And the way to come up with this new stress tensor is to define a so-called pulled back force, dF0. Why we say it's a pulled back force is because we imagine the dF0 in the initial configuration, and if it were to go through transformation, this vector would then end up being dF in the current configuration. All right, which means that dF0 is the inverse of F times dF. So F is a deformation gradient. So if we multiply dF0 with the deformation gradient, we obtain the dF, the real force in the current configuration. So dF0 is sort of an imagined artificial quantity. We call it pullback, or you can think of it like a shadow of dF in the initial configuration. And then we can define a new stress tensor, which is F inverse times P, so that we can express this shadow or pulled back force as the S multiplies with N0 or then multiply with dA0. You can verify this yourself. Basically, here dF equals to P N0 dA0, and dF0 would then be F inverse P n0 dA0, and F inverse P is S, then we have this equals to S n0 dA0. Now I have a new definition of stress tensor. I'm going to substitute the expression of P into the expression of S. Then I would obtain the expression of S in terms of deformation gradient and the Cauchy stress tensor, which we are familiar with. Now you can see that the S, the second polar Kirchhoff stress tensor, is symmetric. It is also defined in the initial configuration completely, which means that it takes in quantities defined in the initial configuration only and export quantities defined in the initial configuration. It has both legs in the same configuration. And this is very nice because it corresponds to the Green-Lagrange strain tensor that we defined earlier on in the kinematics. And this is the tensor stress tensor we use in geometrical nonlinear FEM to define constitutive laws. So basically, in the case of linear elasticity, we would typically write the second polar Kirchhoff stress as a function of the Green-Lagrange strain tensor. So C here is a constitutive matrix which relates the two. Here is a summary of statics. We started off with the Euro term Cauchy stress tensor. Then we defined the first polar Kirchhoff stress tensor, which gives us engineering stress if we multiply it with the normal of a surface in the initial configuration. However, it's not symmetric. Then we move on to define a new stress tensor, which is called a second polar Kirchhoff stress tensor. It has no real physical meaning if you multiply it with the normal in the initial configuration, but it has a nice property of being symmetric, and it is only related to quantities defined in the initial configuration. And it is the choice to define constitutive laws together with the Green-Lagrange strain tensor. Then we have the true stress, which we know that true stress over a certain area equals to the Cauchy stress tensor multiplied with the normal of that area. Then we have the engineering stress, which equals to the first polar Kirchhoff stress tensor multiplied with the normal of the initial area. We have the force, total force acting on a small area, and its shadow or pullback force in the initial configuration. This is an imagined quantity to facilitate the definition of second polar Kirchhoff stress tensor. And then we have the body force densities in the initial and the current configurations, respectively. So you can see the effort behind the mechanics community to go step by step from the current unknown configuration to define everything in the initial known configuration. And all these have been implemented in a very easy to use option in most finite element software packages.